Welcome to Try a Maths Problem today. I recommend you pause the video and try it yourself before continuing on and watching my solution.
We are asked to prove that square root of 2 is not a rational number. To do that, we're going to make the assumption that it is a rational number. So let's talk about what a rational number is. So like I said, let's assume it is a rational number. A rational number is a number that can be wrote as two integers dividing. So a divided by b. And like I said, these are both integers. So I write that as a and b is an element of z. They're just both integers. And they're also the smallest integers they can be. What I mean by that is, instead of like 3 over 6, 3 over 6 is the same as 1 over 2. So whatever two numbers are here, they're the smallest they could be. Because obviously there's infinite number of fractions going this, multiply this by 2 or any number you want. You can get infinite number of fractions that are the same. But we're going to say they're the smallest they can be. And again, we're just assuming, so this works. I'll talk more about that at the end to strengthen up that idea. But that's how we're going to go about this. Okay, what is not a rational number? I'll talk about that as well. Some famous examples is square root of 2, pi, and e. They're not rational numbers. They're numbers we just can never get them with fractions. So square root of 2 is just a handy one we can prove. So let's go into that. When we have a square root, the most common thing to do is just square both sides, and no different here. We're going to square both sides. We get 2 is equal to a squared over b squared. Let's multiply both sides by b squared. We'll get 2b squared is equal to a squared. At this point, we have a leap, a very smart leap. I'm not sure who the first person to prove this. I think it might have been a Pythagorean back in ancient Greece times. But the leap here is to notice that a squared must be even. And that's because it's equal to a integer multiplied by an integer, which is an integer, and then multiplied by 2. And you multiply any number by 2, you'll get an even number. So b squared has to be a number, multiplied by 2, we have to be even. So I can now say a squared is even. Now remember what a squared is. It's a multiplied by a. And that means it's two numbers multiplied by themselves. The only way to get an even number in that case is if a is even. Two odd numbers multiplied by themselves are, or two odd numbers multiplied is an odd number. Two even numbers multiplied is even. Or hell, any even number multiplied at any point is even, and they just happen to be the same. Whatever way we say it, a is even. Okay, but if a is even, that means I can rewrite a is equal to some letter, we'll say c. That's pretty much the definition of an even number. It can be multiplied by 2. Okay, so I'll leave that for a moment. If we put that back into this point up here, and we go 2b squared is equal to, instead of a, let's put in 2c squared. This becomes 2b squared is equal to 4c squared. Divide them both by 2, and we get b squared is equal to 2c squared. Again, c is some integer now. This is very similar to what we have up here, except a squared was on its own here. Now b squared is. So by the same logic I did here, I can say b squared is even. I can say b is even. I can say b must be equal to 2 times some number. And we call that number d. At this point, if we put that back right into the beginning, we break one of our assumptions at the start. Right at the beginning, I said square root of 2 is equal to a over b. But now I know a is 2c and b is 2d. 2 divides 2, this is equal to c divided by d, where c and d are smaller than a and b. But at the start, I assumed that I had the smallest fraction I could get up here. And this breaks that assumption. That's enough. That's enough to prove that square root of 2 is not rational. But to talk about a bit more, square root of 2 equals c over d. I could start this again with c and d And at the end of it, I would get, well, it's also equal e over f, where they're both half the size again. And I could stay going on forever and ever. And if you think about that, that means that whatever number I started with must have been so big that I could get half of it every time, forever and ever. And there's no number that exists that's so big you can half it forever and stay going, except for infinity. And the idea that square root of 2 is equal infinity divided by infinity is a bit ridiculous as well. That's clearly not what we're looking for. So something breaks down. And what breaks down is the idea that we could have wrote this in the first place. Square root of 2 will never be equal to a divided by b, where both of these are integers. So we've proven square root of 2 is not rational.